Think about planning a road trip. What you really care about is the total distance of a route, the kilometers already behind you, plus the kilometers still ahead, the road behind you, a cost you know exactly, the road ahead, a distance you can only estimate. Add them, and you have a hunch about how good this whole route will be. Star search is exactly this idea, turned into an algorithm for finding cheapest paths through a graph. It's the crown jewel of search, uniform cost search, made smart with a heuristic. Let's build it. We're moving through a graph of states, from a start S toward a goal G, and every edge from n to n prime carries a step cost, C. On each node, star keeps track of three numbers. G of n is the cost you have already paid, the cheapest route found so far from the start to n, the road behind you, and you know it precisely. H of n is the heuristic, your estimate of the cost still ahead, from n onward to the goal. This is the guess, the smart part we added last lesson, and f of n is simply their sum g plus h. It's star's estimate of the total cost of the best path that runs all the way through n. Behind plus ahead. Put a spotlight on that f, the cost behind, plus the estimate ahead, gives the estimated cost of a whole journey through this node. Star's entire strategy is to always chase the smallest f, the most promising route overall. One convention we keep from before and lean on all lesson. At the goal, there's nothing left to travel. So h of the goal is 0, which means f of the goal equals its g, the real path cost. Here's the whole algorithm. It is uniform cost search with one change. The priority queue is keyed by f instead of by g. We keep a frontier of discovered nodes and an explode set of finished ones. Step 1. Pop the node with the smallest f, the most promising node in the whole frontier. Step 2. And this is the subtle one. Test for the goal only when it is popped, not when it's first generated. We'll see exactly why that matters. Step 3. Otherwise, expand it. For each child n prime, its new cost g prime is the parent's g plus the edge cost. Step 4. If that new route to n prime is cheaper than any we knew, relax it. Update the child's g and its f. Then loop back to step 1. That single key, f equals g plus h, is the whole engine, and it quietly contains two algorithms you already know, which is exactly where we head next. Picture a dial. At one end, pure cost, uniform cost search, which watches only where you've been. At the other end, pure guessing, greedy, which watches only where you're going. A star sits in the middle and balances both. A star lands right in the center. F equals G plus H. It respects the cost you've truly spent, and it listens to the estimate ahead. That balance is what makes it both fast, like greedy, and correct, like uniform cost. One line of code holds all three. Greedy gambles on the guess. Uniform cost ignores it and plods. Star takes it as counsel, not command. That's the sweet spot. Let's watch it in action. Time to run it. Here is a small map. Start S, goal G, and two ways round, through A or through B. Each road shows its cost. And here are the heuristic values, the little gold H beside each node. S guesses 4 to the goal, A guesses 3, B guesses 1, and the goal, of course, guesses 0. Seed the frontier with the start. F of S is G0 plus H4. So S sits in the queue at 4. Pop S and expand it. Child A gets G1. So f of A is 1 plus 3, 4. Child B gets G2. So f of B is 2 plus 1, 3. The queue now holds B at 3 and A at 4. Smallest f is B at 3. So B is popped before A, even though A came from the shorter first edge. Expand B, it reaches the goal with G equals 2 plus 3, 5. So f of G is 5. But we do not stop. The goal has not been popped yet. A at 4 is now the smallest, so pop A. From her, the goal would cost 1 plus 5, 6. But G already has cost 5. and 6 is not cheaper. So we leave G untouched. Now G at 5 is the only thing left and the cheapest. Pop it. And this time it is the goal. So we stop. The path S star returns is S, B, G at cost 5. The genuinely cheapest route. The expansion order along the bottom. S, B, A, G, together with the return path and its cost, is the whole answer to any A star question. When is A star guaranteed to return the cheapest path? Two conditions on the heuristic, one per style of search. First, admissible. H never overestimates the true remaining cost, H star, at any node. That alone makes tree search optimal. The first goal it pops is the cheapest one. Second, consistent, the stronger cousin. On every edge, h of n is at most the step cost plus h of the next node, a triangle inequality. This is what you need for graph search, where nodes can be reached many ways. Consistency buys two things. Along any path, f never decreases, and so once a node is popped, its g is final. S star never re-expands it. Every node at most once. And the danger, the flip side. Let a heuristic overestimate even at one node, and admissibility breaks. An inflated H makes a good route look expensive, and S star gets scared of the cheapest path. Take our diamond. The true best is S, B, G at 5, but inflate the guess at B to 7, above its true cost of 3, and f of B becomes 9, while f of A is only 4. S star pops a first and can return the costlier S, A, G at 6. One lie, and the guarantee is gone. Here's the real reason A star matters. A good heuristic finds the cheapest path while looking at far fewer nodes. Same graph, two searches. There's a good route S, AG costing 4, and a tempting cheap detour through D and E that leads away from the goal. Uniform cost search ignores the heuristic. It follows raw cost. So the cheap first step to D at 1 lures it in. It pops S, then D, then A, then E, wandering down the dead-end detour before finally settling the goal at 4. 5 nodes expanded. Now S star with an honest heuristic. From S, the detour node D has a big H of 7. Its F is 1 plus 7, 8, while A's F is only 4. So S star never touches D or E at all. It pops just S, A, G, 3 nodes, straight to the answer. 5 nodes versus 3 for the same optimal path. The sharper your admissible heuristic, the more of the graph S star can safely ignore. The guarantee of uniform cost search at a fraction of the work. Your turn. A fresh graph. S to A costs 2, S to B costs 1, A to G costs 2, B to G costs 6. The heuristics are in gold. 2 tasks. After you expand S, what are f of A and f of B? And then, which path does A star return and at what cost? Pause here and work it through. Here's the walk. Expand S. A gets G2, so f of A is 2 plus 2, 4. B gets G1, so f of B is 1 plus 5, 6. A's f is smaller, even though B was the cheaper first step, so A is popped next. Pop A, and it reaches the goal at cost 4. G is now the smallest in the queue, so pop it and stop. The answer is SA. G cost 4. If you got f of A is 4, f of B is 6, and that path, you have genuinely got S star. Trap 1, the big one. Test for the goal when it is popped from the frontier, not the moment it's first generated. In our greedy trap example, the goal was generated early at cost 102, but S star kept going and later found 10. Stop too soon, and you return the wrong cost. Trap 2, an overestimating heuristic destroys optimality. If H is bigger than the true cost even once, S star can be stared off the cheapest route. Admissible means never over. Underestimating is always safe. Trap 3. S-star is not magic on memory. Like uniform cost search, it keeps the whole frontier in the priority queue, which can grow exponentially. A good heuristic prunes work, but S-star can still run out of memory on large problems. And trap 4. When two nodes tie on F, the tiebreak matters. It changes the expansion order. A common choice is to prefer the node with the smaller h, which pushes toward the goal. If a rule is given, use it. Otherwise, state your assumption. Let's bring it home. S-star scores every node by F, the cost already spent, G, plus the estimated cost still to go, H, and always expands the node with the smallest f. It contains two old friends. Zero out the heuristic and its uniform cost search. Zero out the cost and it's greedy. S-star keeps both and balances them. It tests for the goal only when the goal is popped from the frontier, never the moment it's first generated. That patience is what protects the cheapest cost. It returns the optimal path when the heuristic is admissible, never overestimating, for tree search, and consistent, obeying the triangle inequality for graph search. And the sharper your admissible heuristic, the fewer nodes A-star expands. That's the whole win. Optimal paths, found fast. Next, we leave single-agent search behind and ask a harder question. How do you plan when an opponent is fighting back?